In the last class, we studied the procedure to construct a non-binary Huffman code. We saw that the procedure is similar to the construction of a binary Huffman code, the difference being that at each stage of source reduction, we combine R symbols instead of two symbols, where R stands for the size of the code alphabet. And we have also seen that at each stage of source reduction, the source symbols will reduce by R minus 1, and if at the final stage we want that there should be R symbols, then the total number of symbols which should be existing in the original alphabet should be of the form R plus alpha times R minus 1, where alpha is an integer and R is the size of the code alphabet. Now, the only hitch was that if this condition is not satisfied, then we said that we can add some dummy variables with probability 0 and then combine R symbols at each stage of source reduction, and in the final stage when we are getting the codes for the code words for the particular symbol, we ignore the code words for the dummy symbols. Now, let us look at that procedure with the aid of an illustration. Let us say that I have a source consisting of 6 symbols. So, S is given by S1, S2, S3, S4, S5 and S6, and I need to find out a code which is a Huffman code, and the code alphabet is a ternary. So, the code alphabet is 0, 1, 2. So, let us assume that probabilities have been given to us as 0.2, probability of okay. Is 0.25 and P6. So, probability of S2 is 0.05. So, the first step is to generate the non-binary Huffman code for this source with this code alphabet is to arrange the symbols in the descending order of probability. So, S5 0.25, S1 is 0.20, S3 0.20, S4 S6 0.0, 5, sorry, this is 0.01, and finally S2 is 0.05. So, this is 0.05. 1 0, that is x6. Now we have 6 source symbols, and if you look at the expression, this expression will be of form 3 plus 2 alpha. So this 6 is not of this form where alpha is integer. So if I add one dummy variable, then I will get 7, and this can become of the form 2 into alpha is equal to 2. I will get this equal to this. So I add one dummy variable. So let us add a dummy variable as 7 with a probability of 0.0. Now once we have done this, then we combine these 3 elements at this. I get as so I will just indicate, I get here S5, S1, S3, S4, and this is say XC dash, and this is 0.25, 0.20, 0.20, 0.20, and 0.15. Then again I combine this 2, 3 and place it on the top. I get S3 dash as 0.55. This will be S5, that is 0.25, and S1, that is 0.20. Once we have got the 3 symbols for the, because R is equal to 3, now we can allot this as 0, 1, 2, allot here as 0, 1, 2, final allot 0, 1, 2. And based on this, we can find out that the code turns out to be S1 is 2, S2 is 0 to 1, S3 is 0, 0, S4 is 0, 1, S5 is 1, and S6 is 0 to 0. S7 actually would be 0 to 2, but this is a dummy variable, so we discard this. So we get the code words corresponding to our symbols as this, and this can be also depicted in form of a code tree. So the code tree for this would look something like this. So this is your root node. I have here S1, this is my S5, this would be S3, this would be S4, this would be S6, and this would be S2, and this is actually S7, which is discarded, and we follow the convention 0, 1, 2, 0, 1, 2, 0, 1. So once we have the tree, we can also obtain the code words for this symbol by traversing from the root node to the leaf. So S3 would be 0, 0, and S2 would be 0 to 1, which is the same as what we have got it here. Now we can calculate the average length for this code. So the average length turns out to be, there we have one code word of length 1 and 2 code words of length 1 and 2 code lengths of length 2 and 2 code lengths of 3. So, if we calculate that, this will turn out to be 1 into 0.5, 2 into 0.40 plus 3 into 0.15, and this is equal to 0.5 plus so this is 1.70 ternary digits per symbol. So, now this is the optimum 3-array Huffman code for the given source. Now, if we had not followed this procedure, and what we mean by that, if we had not added this S7 and if we had combined 3 and then again 3 and then 2, then we would have got another tree, and another way of combining would be combine 3, then combine 2 and then combine again 3. So, let us look at those tree structures. So, if I combine 3, 3 and 2, then I get it as S5, S1, S3, S4, S6, S2, 0.25, 0.20, 0.20, 0.20, 0.0 and 0.05. So, now without adding any dummy symbol, we will add up, we will get a reduced source by combining the 3 source symbols and then place it here. I will just indicate the probabilities of the new symbols. So, this is 0.35 and then this would be 0.25 and this would be 0.0 and finally this would be 0.20, and then we combine again this 3 and to get a finally 2 symbols 0.65 and 0.35. Now, we can allot 0, 1, 0, 1, 2, 0, 1, 2, and we go from trace the path from here to here. For each symbol, we will get the code word as S1, S2 as 1, 2, S3 as 0, 2, S4 as 1, 0, S5 as 0, 0 and S6 as 1, 1, and this can be indicated in the form of a tree as this is 0, this is 1, this is 0, 1, 2, 0, 1, 2, and this leaves or external node correspond to the symbols as shown here S6, S2. So, here all the code words of length 2. So, the average length will turn out to be as 2 ternary digits per source symbol, and finally we can, so let us call this as average 2, and finally we will follow the procedure as given here. I have S5, S1, S3, S4, S6, S2, 0.25, 0.20, 0.20, 0.20, 0.10, 0.05. So, initially I combine 3 symbols, I get a new source symbol, I place it here, I just indicate the new probabilities, then I place it here, I place it here. These are 0.25, 0.20 and 0.20. Now, I combine 2 elements to get a reduction of the source. So, this is 0.40, 0.35 and finally 0.25. So, in the final stage again I have 3 symbols, but in this procedure in between I have combined only 2 symbols. So, if I allot 0, 1, 2, allot 0, 1, 0, 1, 2 and get the source code for each symbol would be given as follows. One and again I can draw the binary tree for this, and the average length in this case let us call as average length as 3, that turns out to be 2 into 0.75 plus 0.25 is equal to 1.75 ternary digits per symbol. So, the first case we got L as 1.70, second case we got as 2 and the third case we got as 1.75. So, this is the lowest value which we got, and this is the value which you will get if we follow the procedure discussed, where we combine R symbols at a time at each stage of source reduction. So, finally, we reach with the alphabet which consists of only R symbol, and if the initial number of symbols in the source alphabet does not follow that expression R plus alpha R minus 1, then we add some dummy symbols and with the probability 0. So, we have looked at the Huffman coding algorithms for both for the binary case and the non-binary case. Although the Huffman coding algorithm is one of the best known variable length coding algorithms, there are some other lesser known algorithms that can be useful in certain situations. In particular, there are 2 algorithms. One is what is known as Goulomb's algorithm, that is Goulomb's codes, and another one is Tunstall codes. Both these codes are becoming increasingly popular. So, we will discuss these codes next. So, let us take first the Goulomb codes. The Goulomb codes belong to a family of codes designed to encode integer with the assumption that the larger an integer, the lower its probability of occurrence. The simplest code for this situation is the unary code. The unary code for a positive integer n is simply n ones followed by a 0 or n zeros followed by a 1. Thus, the code for 4 would be 1 1 1 1 0, and the code for 7 would be 7 ones followed by a 0. The unary code is the same as the Huffman code for the semi-infinite alphabet 1 2 3. With probability model, Pk equal to 1 by 2 raised to k. Because the Huffman code is optimal, the unary code is also optimal for this probability model. Although the unary code is optimal in very restricted conditions, we can see that it is certainly very simple to implement. One step higher in complexity are a number of coding schemes that split the integer into two parts, representing one part with a unary code and the other with a different code. An example of such a code is the Coulomb code. The Coulomb code is actually a family of codes parameterized by an integer m which is greater than 0. In the Coulomb code with parameter m, we represent an integer n greater than 0 using two numbers q and r. So, n is represented with the help of two numbers which are q and r. Let us see what are this q and r. Q is equal to the truncation value of n by m, and where by definition the lower flow means the integer part of x, and r is given by n minus q m. So, q is the quotient and r is the remainder. So, q take on values 0, 1, 2, all positive integers, and it is represented by the unary code for q, whereas r can take on the values 0, 1, 2 up to m minus 1. If m is a power of 2, we use the log 2 of m bit binary representation of r, but if m is not a power of 2, we could still use log 2m, the upper floor of this number, to represent r. Now, when we represent using this strategy, the number of bits required would be higher than the number of bits required by following the following strategy. So, if m is not a power of 2, we can reduce the number of bits required if we use the following strategy. We represent r by the lower flow of this value bit representation of r for the first two raised to upper flow of log 2 m minus m values. So, for all the values of r which are less than this quantity, we will represent it r by lower flow of log to m bit binary representation, and we will use upper flow of log to m bit binary representation of r plus 2 log to m minus m for the rest of the values. In order to understand this in a much better way, let us take up a simple example. So, let us take an example where a Coulomb code is parameterized by m equal to 5. So, m is equal to 5. In this case, the upper flow of log to 5 is equal to 3. This is the integer which is just larger than this value, and the lower flow of log to 5 is equal to 2. So, the first raised to log to 5 minus 5, that is 3 values of r which are 0, 1 and 2 will be represented, this values of r will be represented by 2-bit binary representation, and the next 2 values of r, which is 3 and 4, will be represented by this will be represented by 3-bit binary representation of r plus 3. So, the q is always represented by the unary code for q. So, if we take Coulomb code for 4, so take 4 I divide by 5, I will get it as 0 multiplied by 5 plus 4. So, in this case q is equal to 0. So, the unary representation of 0 would be 0, and this is r is equal to 4. Since r 4 has to be represented by 3 binary representation of r plus 3, so 4 plus 3 is 7. So, binary representation of 7 is 1 1 1. Similarly, the code word for 14 would be 14 by 5 would give me 2 multiplied by 5 plus 4. So, the quotient is 2, and this by unary representation would be 1 1 0, and the remainder is 4. So, again the representation would be this, and let us take a simple case, another finally 7. So, for 7 this can be represented as 1 into 5 plus 2. So, unary representation for 1 would be 1 0, and 2 is in this range. So, it is represented by 2-bit binary, that would be 1 0. So, I get this is a Coulomb representation for Coulomb codes for different integer values. Now we will look at another code, that is the Tunstall codes. So let us look at a design of the Tunstall codes. Most of the variable length coding algorithms that we have studied encode letters from the source alphabet using code words with varying numbers of bit. What it means that code words with fewer bits for letters that occur more frequently and code words with more bits for letters that occur less frequency. The Tunstall codes is an important exception. In the Tunstall code, all code words are of equal length. However, each code word represents a different number of letters. An example of a 2-bit Tunstall code would be for an alphabet X given by say A and B would be shown in this figure is a sequence, and I have a code word. So if I have a sequence AAA, the code word would be 00. If I have a sequence AAB, the code word is 01. It is AB, it is 10, and if it is B, it is 11. So this is an example of 2-bit Tunstall code for the alphabet A, B. The main advantage of a Tunstall code is that errors in code words do not propagate, unlike other variable length codes such as Huffman codes, in which an error in one code word will cause a series of errors to occur. Now let us take this 2-bit Tunstall code and encode the following sequence. So if I have a sequence given by AAA, B, and let us use this 2-bit Tunstall code. So the first thing is basically you pass this source output sequence into sequences of symbols that appear in the code book. So the first step would be, when I get this sequence, I can pass it as sequences like this. And now for this subsequences in this source sequence, you code it using this 2-bit Tunstall code which we have given here. So AA would be 00, B would be 11, AAB would be 01, 0, 0. Now the design of a code that has a fixed code word length but a variable number of symbols per code word should satisfy the following conditions. So the first condition which it should satisfy is, we should be able to pass a source output sequence into subsequences of symbols that appear in the code book. Second, we should maximize the average number of source symbols represented by each code word. Now, in order to understand what we mean by the first condition, consider codes shown in the table below. I have a sequence here, and the code word as follows. For A, I have 0 0. For AB A, I have 0 1. AB, I have 1 0, and B, I have 1 1. Now, actually this is an example of 2-bit non-Tunstall code. Let us see, if I have a code of this form, then can I represent it the original sequence which I had considered earlier of the form AA, B, AA, B, if we take this source output sequence, and then the first thing we should do is we should be able to pass a source output sequence into subsequences of symbols that appear in the code book. So, if I get this, I can pass it as it like this. So, for 0 0, because available here in the code, I can give as 0 0. For B, I can put as 1 1. But now from this point onwards, I cannot pass this sequence into sequences of symbols that appear in the code book. So, this sequence is uncodable using this particular code, and this is not a desirable condition. So, Tunstall, he gave a simple algorithm that fulfills this condition of able to pass our source output sequences into sequences of symbol that appear in the code book. The algorithm is as follows. So, the first thing is, suppose we want an n-bit Tunstall code for a source that generates identically independent distributed letters from an alphabet of size capital N. So, the alphabet size, that is the source alphabet, is N, and we require to generate n-bit Tunstall code for this source, and this source generates identically independent distributed letters. So, the number of code words which we can have would be equal to 2 raised to n. So, the first thing is we start with the n letters of the source alphabet in our code book. So, we place in our code book the n letters of the source alphabet. Then the next step is remove the entry in the code book that has the highest probability, and then you add n strings obtained by concatenating this letter which you have removed with every letter in the alphabet. So, add n strings obtained by concatenating this letter which we have removed with every letter in the source alphabet, including that letter itself. So, now this will increase the size of the code book from n to n plus n minus 1, and the probabilities of the new entries will be the product of the probabilities of the letters concatenated to form the new entry. And now look through the n plus n minus 1 entries in the code book and find the entry that has the highest probability, keeping in mind that the entry with the highest probability may be a concatenation of symbols. Then once we have found out that symbol with the highest probability, remove this entry and add the n strings obtained by concatenating this entry which we have removed with every letter in the alphabet. So, again you repeat the same procedure of the step 2 of obtaining n strings by concatenating the letter which we are removing from the code book. So, now the size of the code book will become n plus 2 n minus 1. So, each time we perform this operation, we increase the size of the code book by n minus 1. Therefore, this operation can be performed k times, where n plus k n minus 1 should be less than or equal to 2 raised to n, which is the number of code words which we can form out of n bit. Let us take a simple example to understand this. So, if I have a source consisting of 3 alphabets with probability of A equal to 0.6, probability of B equal to 0.3 and probability of C equal to 0.1, then the first thing we do is you start with the 3 entries A, B, C. These have probability 0.60, 0.30, 0.10. In this, the first step, letter A has the highest probability, so remove it. So, what is left out is B and C, and then you get 3 more strings because the size of the alphabet is 3, get 3 more strings which have been obtained by concatenating the letters from this source to this A. So, I will get AA, AB and AC. So, the probabilities would be 0.30, 0.10, 0.36, 0.18 and 0.06. Now, again from here I find this is of the highest probability, so remove it. So, what is left out is BC, AB, AC, and now after I remove this, I get 3 more strings by concatenating the letters from this alphabet to this entry. So, I get AA, B and AAC, and now if I carry out one more iteration, I will get 9 sequences, and since 9 exceeds 2 raised to 3, I have to stop at this point, and now once I have reached this, I can give the code words as 0001, 010, 011, 100, 101, 110. So, these are my code words which I have formed for this sequence, and this would be 3-bit Tunstall code. So, using this 3-bit Tunstall code, you can again code the earlier sequence. So, we have looked at some of the coding strategies, and we have seen that Huffman coding requires, it is the optimal, and it also requires the knowledge of the probabilities of the source sequence. Now, for Huffman coding, which is an optimal coding scheme, if this knowledge is not available, then Huffman coding becomes a 2-pass procedure. In the first pass, the statistics are collected, and in the second pass, the source is encoded. Now, in order to convert this algorithm into a 1-pass procedure, adaptive Huffman coding algorithms have been developed. The algorithm constructs the Huffman code based on the statistics of the symbols already encountered. In the next few classes, we will have a look at the design of adaptive Huffman codes.